We're talking about pretty much what's left. Organic group, carboxylic acids, esters, amines, and amides in this case. These are carbon-containing groups, and then also the last two there are really nitrogen-containing groups to sort of round out our organic education, I suppose. So we're going to talk first, though, about carboxylic acids. And carboxylic acids have the functional group of carbon, oxygen, double bond there, and the OH group. So this is the carboxylic acid functional group. A lot of times in formulas, it will be sort of written as COOH. And when you see that sort of in a formula, it basically represents this carboxylic acid group. Is basically how the connection sort of occurs. Is actually quite a polar type of group that's on there. It's got really two parts that are kind of polar. We got our carbon, oxygen, as we talked about before, kind of a positive charge and a negative charge. And then it also has that OH group, which also is a polar group. So this organic molecule basically has a couple different sort of polar groups happening. Both the carbonyl group, which is the carbon oxygen double bond, and that hydroxyl group, which is our OH bond there. The simplest sort of carboxylic acid you have is what's known as methanoic acid. As you can kind of talk about, drop sort of the last part there of the alkane name and substitute in there the oic acid part. This is ethanoic acid, which has 2 carbons attached to it. This has 1, 2, 3 carbons, which is based off of propane, which would make it propanoic acid. And this has our benzene ring attached to it. So remember, it's got those double bonds in there, which does not make it a cyclohexane, but it is a benzene ring. So that is what's known as benzoic acid, because it is that benzene ring. It is also important, kind of like the aldehyde group, because of this hydrogen here at the end of a carboxylic acid group, it pretty much will be at the end. So it'll be pretty much at one end of the molecule or the other end of the molecule. Again, otherwise you'll have too many bonds to that hydrogen. So that sort of functional group, carboxylic acid, should always be at the end of the molecule because of that hydrogen that's there at the end. Question. So talking about, like I said, we sort of just replaced the E and put oic acid. Will always be, again, that group at the end. We do not need to give the location of where this carbonyl bond is, but it should always be carbon number 1. So whichever side of the molecule it's at, it will take the priority in terms of numbering, and it should be always number 1. And then obviously, if you have other groups attached, we pretty much follow our normal protocol of numbers in alphabetical order. So, you know, if we had something like this, and maybe this, and maybe that, we would still obviously look for the longest continuous carbon chain that has the carboxylic acid group, and that is 1, 2, and 3. Here, you could also get 3 by going kind of straight and then up to that guy. We'll also get you 3, and again, it doesn't matter which way you kind of choose. They both should give you the same answer. So 3 of these guys here is based off of propane. And again, because it has that carboxylic acid group, that would be propanoic acid. Now, this again would definitely be carbon number 1 in this case. This is part of the functional, which means we do need a number right to left in this case. And that means that our methyl group here would be 2. So this would be something like 2-methyl propanoic acid. So we have multiple groups, just like normal. We're going to go alphabetical regardless of the numbering. And again, the important part there is that carbon oxygen double bond will always be carbon number 1 in terms of numbering here with your carboxylic acid. Any questions on that there? Sometimes these guys do have sort of common names, as we may see. This is sometimes referred to as formic acid, and this is also sometimes referred to as acetic acid, also known as vinegar, basically. So some of these early ones will have some common sort of names. It's used a lot. Acetic acid, I would say, is probably used more so than ethanoic acid, but we can use ethanoic acid. Thank you. All right. So here again, actually that was the one I almost just did. We have 1 carbon, 2 carbons, 3 carbons, and 4 carbons, which is where our butanoic acid comes from, as our carboxylic acid group is right there. And once again, this methyl group being at carbon number 3. This is 2,3-dichlorobenzene. So just so we're clear, when we look at this, the entire sort of ring there. And as you can see, because this is the benzene ring, the carboxylic acid group is actually off of the benzene ring there. And that entire thing is the benzoic acid part of it. When we go to number the carbons, we're going to number the ring as to where the carboxylic acid group is attached. And as you can see there, that's going to be carbon 1, carbon 2, and carbon 3. Going clockwise in this case will give us the smaller numbers. If we went counterclockwise, we would have larger numbers, obviously, if we went the other way around to all those groups. And we would name it like normal. So that's carbon 2, carbon 3. There's 2 chloral groups, which is the dichloral part of the name, and then benzoic acid. Any questions on those names there? As I mentioned a second ago, formic acid used a lot, acetic acid, propanoic acid, and butyric acid, occasionally. But I would say out of these 3, these 2 really do come up a lot still. For us, if you are given any of these guys, you could go with methanoic acid and ethanoic acid. You don't have to use, obviously, the common names, but acetic acid and those guys do pop up a lot as you look at these carboxylic acids. So some common carboxylic acids, formic acid, which irritates the skin. That's where you get when your red hand stings you. Vinegar is ethanoic acid or acetic acid. All right, so write the name for this guy. So why don't you take a second there and come up with the name. Okay, let's take a look. So again, longest carbon chain that contains, again, this is our carboxylic acid group right there. Remember that we do need to count the carbon that is there as well, and that is the only carbon. So that's 1, 2, 3, 4, and 5 heading in that direction. That looks like the longest you could get. If you detoured very quickly, you don't end up with 3. If you kind of went over and then down. So 5 is based off of pentane. Because it has the carboxylic acid group, pentane becomes pentanoic acid. And again, this does take the priority in terms of the numbering. So that would be carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. And obviously, as we've talked about, a line with nothing there is a methyl group, 1 carbon and 3 hydrogens at the end of that line. And that would mean that this would be something like 2-methyl pentanoic acid. Questions on that one there? Also, a reminder of how we get to a carboxylic acid. We've talked about, so a reminder that we get to a carboxylic acid really through the oxidation of an aldehyde, right? And we get to an aldehyde through the oxidation of a primary alcohol, right? So our primary alcohol gets oxidized to here. Our aldehyde gets oxidized to our carboxylic acid, right? And again, that is just putting in the oxygen right there to our carboxylic acid. Any questions on that one there? Remember, a secondary alcohol gets us to a ketone, which will not then oxidize to a carboxylic acid. So this is, again, the route that we take, as we talked about previously, to get to a carboxylic acid. All right, so why don't you give some of these names here? Let me just draw some other ones. Why not? Okay, let's take a look. So we'll start our first one here. Longest carbon chain that contains the functional group looks like straight across. You could also get it going straight and then up as well. But either way there, it does look like 3 is a winner. So 3 is going to be based off of propane, which will make this then propanoic OIC acid. This then would be carbon 1 and 2, and there will be our methyl group. So again, 2 methyl propanoic acid. Looking at the next one, once again, the entire benzene ring here, along with our carboxylic acid group, all together there is going to be benzoic acid, as it's a benzene ring. So this guy is going to be benzoic acid. That then means we have a bromine that's hanging out here. Now remember that because it's the benzene ring, the actual carboxylic acid group actually will be hanging off of the ring, if you will. But where that carbon is, where that group is hanging off, should always be carbon number 1 in terms of naming or numbering, I guess. And again, we still want to do the same thing here, either clockwise or counterclockwise to get to the smallest number for that bromine. And in this case, it looks like going clockwise will do that. That's going to be 2 and 3. Again, if you went the other way around, you would have a larger number by the time you got to the bromine. So that's going to be a 3-bromol benzoic acid. Any questions on that one there? The one I just started drawing here on the bottom looks like, actually, if we just go straight across, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, if I count correctly. Carbons in a row there that has our group on it, and 6 would be based off of hexane. So then this would then be hexanoic acid. Once again, wherever that carboxylic acid group is, that is going to be your first carbon. So this then would be 1, 2, 3, 4, 5, and 6. That means alphabetical here, B before C, I think. So that is going to be 4 bromol, 5 chloral. Maybe I could join them up. Hexanoic acid. Any questions on any of those names? Yeah. I should go alphabetical order, so B before C. So just like anything else, pretty much the group should always be should always be put in their alphabetical order. And that's regardless of the number. So even if the numbers are larger, but alphabetically, that guy should come first. He should still come first. And also irregardless of like a prefix, like if there's 2 of them, di or tri in the particular molecule. So you just go by the actual name of the group. Other questions? All right, let's draw some here. Draw 4-chlorohexanoic acid. Draw 2-ethyl, 3-methyl. We'll do pentanoic acid. You could draw the condensed. You could draw the line structure. Why don't you do both? Why not? So first off, oic acid tells us it's a carboxylic acid. The hex part there, which is hexane, tells us we need 6 carbons. So once again, that is where you want to start, just with the 6 carbons. And again, since you're drawing it, you could put the carboxylic acid group on the left or the right, but it should definitely end up at the end, as we talked about, because of that hydrogen. So I'm going to put my group on the right-hand side here, which I guess is over there for you guys. So that is going to be my carboxylic acid part. And again, you can put it on the other side if you wanted to. So that basically takes care of this. Because I chose to do it over there on the right-hand side, that definitely now turns this into carbon number 1 in terms of numbering. And then I would go to carbon number 4, which in my case would be right about here. And I would have put a chlorine at carbon number 4. And just like everything else at this point, everything else will be hydrogens to get carbon to 4. So we're going to need a couple of hydrogens there. We will need a couple there. We'll need one there. We'll need a couple there, and we will need 3 there. Any questions on that one there? Now we're also going to draw the line structure. So you really could start the same way. You just start with your 6 carbons. And again, you could do the zigzag there, probably count more than I did there. 1, 2, 3, 4, 5, and 6. Once again, here you could put it at either end. So in my case, I'll put it over here. I'm going to draw a line, but I am going to put OH there because if I didn't, then that would now be another carbon, right? That also means that I should have my double bond hanging out right there. I should still have the correct number of carbons. I'll just put a little highlight, hopefully. 1, 2, 3, 4, 5, and 6. So again, make sure that you sort of attach it that way. In this case, once again, that's going to be my carbon number 1. So I want to go to the 4th carbon there, which would be, that's 1, that's 2, that's 3, and then that's 4. And I'm going to put a Cl. Yeah. Any questions on that one there? Okay, looking at the one I made up there, once again, we see oic acid tells us carboxylic acid. We got 5 carbons in this case for pentane. 1, 2, 3, 4, and 5, I think. Once again, we need to incorporate that carboxylic acid group on either end. So I'll again go over here to the right on mine. That takes care of this. That means, once again, that's going to be carbon number 1 for me. And a carbon number 3, which would be right around here, we have a methyl group. And at carbon number 2, we have an ethyl group, which is a 2-carbon group. And now we can fill in our hydrogens. This guy needs 1. This guy needs 2. That one needs 3. That one needs 1 only. 2 and 3 there. Any questions on that one there? Again, line structure, we'll start with our 5 carbons. So 1, 2, 3, 4, and 5. And again here, however you want to do it, you could draw the line. And you can even put the double bond going down. It doesn't really matter. In this case, this would be carbon 1 for me, which means that carbon number 2, which should be right next door, I have my ethyl group. So if you want to do something like that. And at carbon number 3, it was, I believe, we have our methyl group, which would be right there, something like that. Yeah. Any questions on drawing, naming carboxylic acids? Yeah. So let's talk about some properties of carboxylic acid. They are, much like the name implies, they are acids, so they do behave like acids. They will actually make a salt and water, like we talked about when we talked about acid and base reactions. They will react with a base and make basically a carboxylic acid salt and water. They also are, as I mentioned earlier, very polar. They have 2 polar groups, which means up until this point, pretty much the most polar group that we've seen is our alcohol. And remember that because alcohols have this polar group, it typically has pretty high boiling points and melting points because it's able to hydrogen bond. With a carboxylic acid, it actually is one of the few things that can beat an alcohol in terms of boiling points and melting points. And that's because it can actually hydrogen bond with itself because of the carbon-oxygen double bond and the OH group there. It could do a little bit of a hydrogen bonding action there. I'll just draw something like this. And between the positive, this, it could do that. It also can do a little hydrogen bonding there, and also like through here and our oxygen over there. So it actually can bond in 2 places with itself, make kind of like a dimer. And that means that a carboxylic acid actually will have a much higher boiling point or melting point than an alcohol. So carboxylic acid could actually beat the alcohol in terms of boiling point and melting point, and that's because it's held together by those really strong hydrogen bonding forces, which means it takes a lot more energy to break them apart from each other to get them into the gas phase when they boil, and that results in a much higher boiling point than what we see. It also allows them to be fairly soluble in water because, again, they pretty much have two locations where they can interact with water through hydrogen bonding. They could interact at the carbon-oxygen double bond. They could also interact at the OH group on that carboxylic acid sort of functional group. So it gives it a lot of places where that's the carbon-oxygen double bond, that's the OH group, gives them many places to interact with water, which means that they are fairly soluble in water. But they are like a lot of organic compounds that if you kind of build out a bunch of the carbons and hydrogens, so that carbon-hydrogen part of it gets really large, the solubility pretty much decreases down to nothing. So around 5 or less carbons, they're going to be very soluble in water. But if you get too many carbons involved, again, if you have this carboxylic acid group, but you have a ton of carbons, I'll just draw a straight line to represent a bunch of carbons, you're just going to have this big non-polar part that's going to get in the way of water being able to get in there. It's also going to make that molecule really too big for it to kind of fit nicely with water to kind of be soluble in it. So you really do start to see the solubility pretty much drop off to nothing as you get above sort of 5 carbons. And that's what we see on this table as we start building out, pretty much getting into slightly soluble, which is pretty much like being non-soluble. So soluble pretty much means it's going to mix. Slightly soluble and insoluble, kind of very similar to each other. Like a little bit will mix, but pretty much most of it's not going to mix when it gets into slightly soluble. And that again happens right around 6 or more carbons is where we start to see the solubility start to really decrease. Now, because they are really acids, they could do a basic acid-base reaction that we've talked about before. And obviously, this is acetic acid or ethanoic acid. And in this case, it's going to be the acid. Our water here is going to be the base, and it's going to send its H plus over, just like a normal Bronsted-Lowry sort of definition of an acid and a base. The result of that is pretty much what we get, like we talked about with an acid and base reaction. We get a salt and some water being formed in a lot of cases, but in this case, we actually will get H3O plus being formed here. So what they'll actually make are these what are referred to as carboxylate ions, or carboxylic acid salts, they're sometimes referred to. So you'll have this ethanoate ion, which we're not going to worry about naming the carboxylate ions, but they basically will make this sort of salt sort of guy in the solution. So write a balance equation for dissociation of butanoic acid in water. So butanoic acid is here. That is 4 carbons, 1, 2, 3, and 4. Just making it our butanoic acid. Dissociation in water just means that it's going to basically send this H plus over, going to make H3O plus, which means it's an acid, and again, our salt. The only thing that basically is different between the carboxylic acid and the carboxylic acid salt or the carboxylate ion is it lost an H plus. So very similar to what we talked about with Bronsted-Lowry definition of acid and bases and conjugate acid bases. The only difference is 1 H plus. So that's sort of very similar to what's going on here. Again, if you put the H plus back onto this guy, you get your carboxylic acid. Obviously, if you take it off, you get your really conjugate base in that case is basically what that is, just like the Bronsted-Lowry definition. Now, as I mentioned a little bit earlier, and I sort of jumped the slide there, but when they do react with a real base, like something like sodium hydroxide, you do get a salt in water. And it's the same really reaction that we talked about with acid and bases. The H plus from the acid, the OH minus from the base is going to make our water that is formed. And basically, this guy will lose its H plus, which makes it 1 more negative. And this is what makes it a salt, which means it has just a sodium or something like that to balance out the charge. And this is our salt and water that is made in this particular case. So these are products of a basically acid-base neutralization reaction. So if you take a carboxylic acid, react it with a strong base, you basically will get a salt and water. And these are preservatives that are used sometimes, and also flavor enhancers and things like food. We're not going to name the salts, so just in case you're curious, you basically replace the ic acid with ate. So instead of benzoic acid is potassium benzoate, but we're not going to do any namings of salts in here, so you don't have to worry about it. Carboxylic acid salts, they really are ionic compounds. They are solids at room temperature. They have high melting points and usually are soluble in water because they're a salt. They're basically an ionic compound. Most ionic compounds are a lot of times soluble in water because ions and water work really well with each other, because the negative side of water basically attracts the positive side of an ion, or a positive ion. And the positive side of water is attracted to the negative ion. And that is, as we talked about, I think in an earlier chapter, really how things dissolve in water, right? Ionic compounds, basically the ions break apart, they get surrounded by water, and they dissolve. Same sort of thing happens here with our carboxylic acid salts. All right, so as I mentioned before, they're used as preservatives and flavors. So you can find these things in cheeses, also in jams. Monosodium glutamate was added to meat and stuff like that. All right, so just to look at this one here, once again, it is our acid, which is our carboxylic acid. This is our strong base. Going to do our basic acid-base reaction here. We're going to make water from the H plus and the OH minus going to come together. And again, basically the sodium ion will kind of come over here to make our salt. So once again, it is a salt and water in this particular case. Yeah.
On the other one, reverse out of the H. How is it that this one can't be reversed the other way? Here,
Are we talking about an earlier reaction we were looking at?
yeah. So the reaction can only go one way on.
Yeah. So I think I know. Let me go back to what I think you're asking. Yeah. So in this case, what we're looking at here is basically a reaction between an acid and a base, basically. So we're getting an actual reaction is taking place. What we were really looking at earlier, which I think is what you might be referring to, which is this one here. Yeah. Yeah. Okay. So what this one really is really just the acid breaking apart into ions in water and solution. So what this actually is a weak acid, which means it's actually a weak electrolyte, which is why you do see these arrows heading in both directions. And it would be the same as, for example, if we took something like just HF, which is a weak acid, we could show that breaking apart in solution as H plus and H plus and F minus. There we go. And it would have these reversible arrows again, because that's a weak acid. You could also show this, which is also sometimes referred to as the dissociation of an acid, which is just a fancy way of saying it breaking apart in solution, by inserting water into the equation. And water here is really acting as a base in this case, which is the same reaction as we see up here. And in this case, we get H3O plus because we included water, and F minus. Both of these reactions are basically the same reaction. It's really nothing more than when you put the acid into like a solution, it's not really reacting with anything other than it's happening here. And because the HF is a weak acid and most of these carboxylic acids are also weak acids, they're weak electrolytes, and that's why we have that kind of reversible reaction that's taking place, going in one direction and back in the other direction. When we actually react a carboxylic acid, which is a weak acid, with a strong base, which is what's happening here, it's basically a one-way reaction. and that's basically going to produce what's on the other side in this particular case. So technically speaking, this what we're looking at here is sort of a real reaction. It's sort of happening, two things sort of reacting. The other one is just two representations of just the acid itself, just kind of breaking apart in solution, not necessarily reacting with anything other than water, which is always in a solution. But this is really two different sort of compounds coming together reacting, which is why it's a one-way sort of street on that arrow. Other questions? So carboxylic acids are also part of a metabolic process in our cells. As you can see here, here's pyruvic acid, which is a carboxylic acid. There's the functional group right there. And it also is part of the citric acid cycle, the Krebs cycle. And again, this is a very commonly the way, for example, we'll also see it when you look at proteins and amino acids. That's very commonly, again, how the carboxylic acid group is written in a formula. Once again, that represents the carbon-oxygen double bond in the OH group that's happening here. All right. So let's talk a little bit about esters, which are another organic chemistry group. And they are really made from the combination of two things, and two things that we talked about. They are made really from the combination of a carboxylic acid and an alcohol basically come together. So how we make an ester, as we'll see in just a second, is really you take a carboxylic acid and you take your good friend, an alcohol. There we go. And the R is just a carbon containing group. Like take out water. Yeah, so you take out some water. And then pretty much you just kind of squeeze everybody together on opposite sides of where the water box is. And you end up with this ester here. And that right there is our ester. And this is, as we'll see in just a second, was referred to as a esterification reaction. You basically take out water, squish everybody together. So an ester has a functional group that looks like a carboxylic acid, except it is not have an OH group. It's actually a oxygen to carbon connection. So it is this connection right here. And again, very similar to the carboxylic acid group, because frankly, it's made from a carboxylic acid, but it does not have the OH group. It has the carbon. So esters are synthesized from, as I just mentioned, a reaction of a carboxylic acid with alcohols. They're also found in fats and oils. So when you talk about lipids and fatty acids, a lot of those guys come together to make an ester. They're responsible for a lot of like aromas and flavors that you associate with things like bananas, oranges, and strawberries. And again, if you basically take out a water, you will get your ester here. So how are these guys sort of named? Because they really do come from kind of two parts, it does play a role in how it's really named. And you could think of it as really being those two parts. So going away from the carbon-oxygen double bond to the single bonded oxygen, that's always the alcohol part of an ester. Going past the or towards the carbon-oxygen double bond, it's always the carboxylic acid side. And that's really important in terms of how we name esters, sort of which side you're talking about. But again, kind of going away from the single bonded oxygen towards the double bonded oxygen, always the carboxylic acid side, and heading away from the double bonded oxygen is always going to be the alcohol side. So as I mentioned before, it is an esterification reaction, and basically we just take out water and squeeze both sides together. And we go from ethanoic acid and methanol to something known as methyl ethanoate. And that is pretty much how we go about naming this guy. So if we look at the ester by itself there, Once again, if we kind of put a line right there, going towards the bonded oxygen, that's the alcohol part. Going towards the double bonded oxygen there, that is our carboxylic acid part. And it is the alcohol part that's named as a group. So that is a CH3, which is a methyl group. So that is where the methyl comes from. And this part here, which is our carboxylic acid, is based off of, you can think about it one of two ways. You can still think of it as ethane. You can think of it as ethanoic acid, however you want to do that. But basically, if you want to think about it as ethane, you could drop the E and put O8 at the end of it. So these guys get like the O8 at the end of the name. So that is ethane, which becomes ethanoate here. So that is methyl ethanoate, which is a ester. And again, they always have those two parts, and we always basically make water when we put those two guys together. And pretty much all you have to do is start copying from here and continue to copy to here to get to your ester in this case. Any questions on that there? So here's another example. Again, we're just going to take out water, and sometimes it helps to back these guys up to each other. And now we're just going to pretty much copy exactly what is there. Obviously, we're going to take the water out of it. So that's a CH3O. That's a CH3O. And then coming to the other side, that is an OCH2, CH2, CH3, OCH2, CH2, CH3. So again, basically just take the water out and squeeze everybody together. Nothing else changes. So don't do anything weird or anything like that. Just simply squeeze them together, take the water out, and you'll have your ester. Now, again, if we look at this ester and we want to get to our name, as we just talked about, we would look at it right here between the carbon and the single bonded oxygen. And once again, going towards the single bonded oxygen is our alcohol part. And going towards the carbon oxygen double bond or away from that side would be our carboxylic acid part. So it is the alcohol part that's named as a group. So that's 1 carbon, 2 carbons, 3 carbons. So that is where the propyl comes from. Coming to our carboxylic acid group, that is 1 carbon, 2 carbons, which is based off of ethane. Put the O8 at the end of it, and this becomes propyl ethanoate. Any questions on that there? All right. So why don't you do this one here? Do propanoic acid and methanol. And why don't you also do let's do hexanoic acid plus we'll do propanol. We'll do ethanol here. We'll do ethanol. All right, so draw the esters for each of those, and then also so we're going to draw it again based off of the name. So oic acid tells us carboxylic acid, and propane tells us it is basically 3. Once again, we'll need that carboxylic acid group at the end. And here we'll just put our appropriate hydrogens. Methanol is based off of methane, which is 1 carbon. OL tells us it's an alcohol. And in this case, whenever you got a carboxylic acid and alcohol, it's probably best to kind of turn the alcohol perhaps around just to kind of line them up so you could kind of see maybe the water part of it, and it just makes it easier to kind of finish drawing what you need. So because I did that, I now have really my water kind of part together. Doesn't really matter how you take out the water, but you just need to take out water. So OH and an H will do that. Do the HHO, it doesn't really matter as long as you leave one oxygen there. That is going to get us our water that's going to come out of that box. And now again, we're just going to copy exactly what is there, following right here, and then putting this guy together. So just copying exactly what's there. We got a CH3, we got a CH2, we got a carbon oxygen double bond. I'm going to skip the box that I took the water out of. And now that's going to give me my ester connection right there to my CH3. Let's get any questions on that there. Now, in terms of naming, once again, we could kind of split our ester right where those two actually come together. So pretty much right where you took out the water, once again, going towards the single bonded oxygen will always be your alcohol part, which is basically the group name. And that again is a 1 carbon, so that's a methyl. Going the other way, kind of towards the carbon oxygen double bond is going to give you your carboxylic acid part, which is really the base of the name. And in this case, that's 3 carbons, which is based off of propane. We drop the E and put O8 at the end of it. So this guy here should be methyl propanoate. Yeah. Any questions on that one there? Doing our one I made up there, which is hexanoic acid. So that's going to be hexane, and oic acid going to be our carboxylic acid. That's going to be a 6 carbon carboxylic acid. Carboxylic. My carbon, hydrogen's in, should end up something like this. So now, it's literally all you got to do is put a box of water, and however here, you could take the water out there, and that is going to give us the water. And once again, we can start there and just continue on, and obviously take out the box. So if I did that, we would have CH3, CH2, 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 carbon oxygen double bond. Now going to my oxygen to my CH2, CH3 in this case. And again, you can obviously put it the box around the other way like we did before, however you want to do it. So as long as you take out water, you'll be in good shape. All right, so naming this guy here, once again, we want to kind of divide this into 2 parts right there at the carbon oxygen single bond. Again, going towards the single bond, going to give us our group, which is 2 carbons. So that's going to be an ethyl. And going the other way, we obviously have our 6, 1, 2, 3, 4, 5, and 6. So that's going to be our hexanoate. So this is going to be an ethyl hexanoate. Yeah. Any questions on any of those there? Again, this reaction is what is referred to as an esterification reaction. Carboxylic acid, alcohol, water goes out, squish everybody together. You make an ester and you have smells. Bless you. Which I think you'll do this week. I think you'll put them together and then maybe smell them. I'm not sure, but don't smell too much. Right. All right. So obviously we kind of named esters there as we were talking, but again, that's really how you want to think about it, as kind of the 2 parts, the alcohol part and the carboxylic acid part. And once again, the carboxylic acid part really is the base of the name. You add I personally like to go back to the alkane name. myself, drop the E and put the O8 at it. But again, you could also, drop the IC from the carboxylic acid name and put 8 at the end of it. So however you want to remember it, will get you there. And again, the alcohol part is where we get our group that's named from it. Now, some esters do have IUPAC names and common names. So that is ethyl ethanoate, also known as ethyl acetate, because it comes from acetic acid, which is ethanoic acid. Methyl propanoate, methyl propionate, and ethyl benzoate here as well. So this is really our benzoic acid, right? So that is our benzoic acid part. And that again is where that benzoate sort of name comes from. All right. So aspirins and salicylic acid and acetic acid coming together basically will make aspirin. And that is our ester, our carbon, oxygen double bond, and our oxygen happening there. And that is basically from our water coming out here. Chase the water out, put it together, and you make aspirin. Very common experiment. People used to do a lot in chemistry, long experiment. But basically you can make aspirin pretty simply by that two things coming together, making our carboxylic acid group and our alcohol group coming together to make our ester. All right, so why don't you do this name? Why don't we draw a couple more here just to make sure? Let's do and why don't you draw, let's do propyl butanoate, and let's do yeah, let's take a look. So we'll start with this one here. So once again, always when you recognize, hopefully the ester sort of bond going on there, that is also where you should recognize you should break it between the carbon oxygen single bond. Once again, in terms of naming, going towards the single bonded oxygen, that is going to be our alcohol part and really our group part, which is 2 carbons in this case. So that's going to give us an ethyl. Going the other way with our double bond, going through the double bond really to the other side, that's going to give us 1, 2, and 3 carbons, which is based off of propane. Drop the E and put O8 at the end of it, and that'll give us something like ethyl propanoate. Yeah. Any questions on that one there? Now, on the one that I drew up here, I just kept drawing lines to see what I ended up with. But this part right about here is really our ester group, and that means that's a carbon right there, right? So if we broke it right there, once again, going towards the single bonded oxygen, that would actually give us 1, 2, 3, and 4 carbons, and that's based off of butane, and it's going to be named as a group since it's the alcohol part. So that's going to be a butyl group there. Going the other way, we don't want to forget this guy, which is a carbon, 2, 3, 4, and 5. That's based off of our carboxylic acid heading in that direction. 5 going to be pentane, pentanoate. Yeah. Any questions on that one there? All right, so drawing, we're going to go backwards here. Once again, the O8 tells us it's an ester, and the butane tells us really it is 4 carbons. I would say slightly different on these. Once you recognize that it is an ester, that's actually probably where you want to start with in terms of drawing it. So you just want to kind of draw the ester group. So that is what I'm going to do here. And again, you can put the oxygen either side. It doesn't really matter. And that sort of gives you your sort of ester group that you need. Now you can really build what else you need, which is, in this case, that is propyl, which is the alcohol part. And remember, the alcohol part always goes to the single bonded oxygen side. So propane is 3 carbons. So I'm going to do 3 carbons. The butane part here for the O8 is the carboxylic acid part, which is 4 carbons. And the important part, though, is you already put a carbon here, right? So I actually only need 3 more here, right? To make sure I have the right amount. Now, just like everything else is going to be hydrogen. So that's going to be 3. That's going to be 2. That's going to be 2. That will be 2. That will be 2. And that will be 3. Any questions on that one there? So same thing here. The O8 tells us it is tells us it's an ester. So again, that is actually where I'm going to start with, is actually just the ester part of it. Again, the methyl part comes from the alcohol. And since I put the single bonded O there, that means I just need 1 carbon. Pentane part there comes from our carboxylic acid, which means I need 5. I got to remember I already have 1 here. So that's going to be 2, 3, 4, and 5. Thank goodness I ran out of room there. And everything else here will be some hydrogens going on. Maybe 2 there would be good. 2, and a 3. Any questions on how to draw these? So I would say with these, I would probably start with that ester group and then just build your alcohol side, build your sort of carboxylic acid side, and don't forget that you already have a carbon in the middle there. And because very common people just go put an extra carbon cut on that side. Any questions on how to draw esters here? Professional esters. I like it. All right. So esters, as we've been talking about, are a lot of the fragrances and perfumes, flowers, fruits. They are volatile, which means they do go into the gas phase really easily, which means you could smell them very easily. So here are some of the ones. So for example, here, that's propyl ethanoate, which is what we see in pears, bananas. We got oranges, pineapples, and so forth, but they all again have that ester group. And once again, in each of these cases, going towards the single bonded is our alcohol part, going towards our double bond is our carboxylic acid part there. And again, we would break these guys apart right about there. And again, towards the single bond alcohol. And going the other way, our carboxylic acid. Again, each of these would be made by doing a esterification reaction, which means if you add some water to it, you could probably break it back apart into its carboxylic acid and its alcohol in that case. All right, so finish out, let's draw these 2 here. 3, let's take a look since we're getting to the end here. So again, the name helps us understand what we're looking at. So that is a carboxylic acid based on the name. So that will just roll like normal. So butane is 4 carbons. Once again, we do need to put our carboxylic acid either on the right-hand side or the left-hand side. It is your choice. I went to the right-hand side, which once again locks me into this being carbon number 1. Which means, again, at carbon number 3, we should have the Br. And then we're just going to fill in our hydrogens like normal to get carbon to 4 bonds. And now we got it, I think, in this case. Any questions on that one there? The ethyl propanoate, again, the O8 tells us it's an ester. And once again, on this one, as we just talked about, I personally would start with the ester connection just to have it all kind of set up correctly. Once again, the sort of group name is the alcohol part, which should always go to the single bonded oxygen. And that means that I need 2 carbons on this side for me. Again, if you flipped it around, you would have it on the other side. And the propane part here will be from our carboxylic acid part, which should always go to the double bond part. And that means that I need 3. I do need to remember I already have 1 there, so I actually only need to write 2 more. And in this case, we're going to fill in our hydrogens to get to 4. And here and there. Any questions on either of those there? All right, we'll lay it up there for today.